One challenge we have when designing wireless networks is dealing with reflection. Reflection is when a wireless signal bounces off objects. Some objects, like desks or metal, may bounce signals better than others, and the signal may bounce differently at 2.4 gigahertz than 5 gigahertz. If there's too much reflection, you may find that the signal is weaker than you might expect. But a little bit of reflection can actually be useful, especially if you're taking advantage of multi-path interference with MIMO. This reflection may be something that you can work around by changing the direction of your antennas or where your antennas might be positioned. And again, reflection may not be as big of a problem if you're taking advantage of MIMO in 802.11n or multi-user MIMO in 802.11ac. Wireless signals can also suffer from refraction. This is when the signal is passing through an object and it exits that object at a slightly different angle. This might affect data rates, especially on connections where you're dealing with very directional signals. For example, outdoors between two buildings where you have long-distance links, and those links might have fog, water vapor, or temperature changes that might affect the refraction rates of those wireless signals. If a wireless signal isn't reflecting off of an object, then it may be absorbed by the object. That means the wireless signal is going to pass through an object and lose a little bit of signal as it passes through. This can be a problem as the wireless signal goes through walls or windows and it has less signal as it passes through on the other side. Different objects will absorb differently as the frequencies change. So you may find 2.4 gigahertz has a very different absorption rate than 5 gigahertz. This is one of the reasons we put wireless antennas on the ceiling. That way the wireless signal can get to you without going through or being absorbed by other objects. As we saw with our wired troubleshooting video, we should always be concerned about latency. And this is a problem also for our wireless networks. The latency is the delay between transmitting information and receiving the response. We might also be concerned about jitter on our wireless networks. Jitter would be a deviation from a predictable data stream, very commonly associated with real-time communication like voice over IP. Whenever you get on a wireless network, there's additional opportunity for interference and signal issues because anything could be conflicting or interfering with that wireless signal. This would cause lower data rates and it will cause retransmissions and loss of data. You might also run into challenges with latency and jitter if the network is very busy. If you're over capacity and have many different devices communicating, there may be slowdowns as more and more people join that wireless network. Just as we have attenuation on copper and fiber networks, we also have attenuation on wireless networks. As we move farther away from our access point, the signal gets weaker and weaker. And you can usually measure this by looking at the signal strengths on your device or using a Wi-Fi analyzer. To help avoid excessive attenuation, you may be able to boost the signal strength on the access point itself. Not all access points have this option, but this may allow you to get a larger range out of your existing wireless access point. If the device you're on supports an external antenna, you may be able to use one with a higher gain. That will allow you to capture more of the signal, so even if there is attenuation, you're still able to receive and transmit on that network. And of course, the closer you are to the access point, the less attenuation you're going to have. So you may find that moving closer to your access point greatly improves the performance of your network connection. Interference on a wireless network means that something else is using the same frequencies that we're trying to use to communicate on this wireless network. Sometimes this is predictable interference. It may be a microwave oven or a fluorescent light, and we can easily turn off the light or turn off the microwave oven, and the interference will go away. But sometimes the interference is something that we can't predict. You may be in an office building with many other companies, and all of those companies have their own wireless networks, and you don't have a way to manage their access points so that there's no interference with yours. One way to look at interference statistics is to view them on your Linux or Mac OS X workstation with the netstat command, or you may want to use Performance Monitor in Windows to monitor those statistics over time. The type of wireless antenna that you use will depend on the reach and the scope of your wireless network. If you're trying to cover wireless networks on a single floor of a building, you'll be using a different antenna than if you're trying to connect two buildings to each other. For example, we could use an omnidirectional antenna like the one we see here. We'd put it up on the ceiling, and it has an equal amount of signal that goes in every direction. If we're trying to connect to buildings, though, we might want to use a directional antenna, where all of that wireless signal will be directed in one single direction, and you'll have the best chance of connecting those two buildings together. You might also find that your access point allows you to connect different types of antennas, so you may choose exactly the right antenna for the type of network that you happen to have. You might also want to make sure that you're putting these antennas in the right place. If you put access points too close to each other, you may find that those frequencies will interfere with each other. Or if the antennas are too far away from your users and there's other electrical devices causing interference, then you may find there's slower throughput than what's expected. You might also want to check all of your access points to see if they're using the frequencies and the channels that you're expecting. You want to be sure you have the best coverage for your network, but you also want to be sure that you don't have any conflicts with any of those channels. For example, you might have an office building floor. You're trying to find the best coverage for all of these rooms and all of the areas on this floor. So you might use a number of different access points with omnidirectional antennas, and you'll configure the access points to be on different non-overlapping channels. That way, no matter where you are on this particular floor, you have connectivity to the wireless network, and you can make sure that none of these channels are going to conflict with the others. This can be a challenge with 2.4 gigahertz networks because there's only so many non-overlapping channels available. For example, on this network, you can see someone is on channel 6 and another access point is on channel 11. And those two access points are not overlapping with each other. But then someone else may turn on another access point at channel 8, and now you have a frequency conflict with both channel 6 and channel 11, and now no one's network is going to be running at the best efficiency because of all the interference that's been introduced. One problem we really have with wireless networks is there's only so much capacity available. Only so many devices can be communicating over these very narrow frequency ranges that we have for wireless networks. So if you have too many devices on the same wireless network, you may run into problems with device saturation. If you have the option of using 5 gigahertz frequencies, you have many more frequencies available to use, and you may find that overcapacity isn't as big of a problem. You might also run into problems on wireless networks with bandwidth saturation. This might be many people trying to transfer many files all at once, and you find that the wireless network simply doesn't have the bandwidth to support all of those transfers simultaneously. When we're managing our own wireless network on the floor of a building, we don't usually run into overcapacity problems. But when you get into very large environments such as conference centers, airports, and hotels, you may often find the wireless network is not running as efficiently as you might have hoped. We have a number of different 802.11 wireless standards, and some standards might use different frequencies than another standard. One thing that we have to make sure is that the devices that we're using are going to be matching the frequencies available on that access point. Sometimes you may run into problems where a client on the network is communicating to the access point, but over a slightly different frequency. You may want to check and see if someone may have manually configured a channel on their wireless device instead of having it set to the default, which is to automatically match what's on the access point. And you may also find that mixing different standards on the same wireless network may cause the network to not be as efficient as possible. For example, if you have an 802.11n network and you've configured it to allow legacy 802.11b devices, you'll have additional information in the frame and additional frames that have to be sent, which will lower the overall efficiency of the network. Every access point has at least one service set identifier, or SSID, configured inside of that device. This designates the name of the wireless network that we would be connecting to. And if this is on your corporate network, it may be very obvious what SSID is associated with your particular network. But sometimes this can be a challenge. You might bring up a list of available networks, and it may be the public Wi-Fi internet, the guest internet, or the internet SSID. Which one do you connect to? Some of them may be associated with your access points. Others may be associated with access points that are not part of your network. You may want to confirm what the correct SSID is and make sure that all of your users are connecting to the right wireless network. Unless a wireless network is completely open to the public, you usually have to provide some type of authentication to gain access to a wireless network. And there are many different ways to provide that authentication. If you're finding that you're not connecting to the wireless network, it may be related to this authentication process. So you may want to make sure that you're using the correct credentials to gain access to the wireless network. Sometimes this is simply a shared passphrase. Everyone is given the same phrase, and they use that phrase to connect to the wireless network. This is very common in a small office or home office, but it's not very common in a large enterprise environment. In the enterprise environments, we prefer using technologies like 802.1x. This is where you would configure your workstation to authenticate using your normal credentials. And those would be credentials that you would only know. Everyone would use their individual credentials, and that gives them access to the wireless network. This means there's no shared passphrase that you would pass around, and you can be sure that if somebody is gaining access to the network, that they use the correct credentials for your organization. If you do have 802.1x being used for authentication to your wireless network and someone is not able to gain access, you may want to check the client configurations for their wireless device and make sure their wireless device is using 802.1x as well. Since our wireless signals are going through the air, it's always important that we encrypt all of the communication we send over these wireless networks. And whenever we're connecting a client to the wireless network, the client's encryption must match what's set on the access point. This isn't usually a problem because most of our devices these days are using WPA2 as the encryption type. But if you have any legacy equipment that does not recognize WPA2, those devices may have problems connecting to our modern wireless networks. Because of security issues associated with earlier encryption types, you may want to make sure that everyone is using at least WPA2 on both their devices and your access points. One good overall statistic to see just how much interference may be occurring on your wireless network is your signal-to-noise ratio. The signal is the normal communication that you want from your wireless network. The noise is interference that you might get from other devices and other wireless networks. And you would like to have a very large ratio between the signal and the noise. You would like to have much more signal than you're having of noise on your network. If you had as much signal as you had noise, it would be a 1-to-1 ratio, and it would be very difficult to communicate over that wireless network. Here's the signal-to-noise ratio on my network. You can see the signal is designated by this green line on my wireless network, and the noise is the dotted line. So you can see the noise is way down here at the bottom at negative 90 decibels, which is a small amount of noise considering all of the other signal that's going through my network.